Imagine this. You're in a self-driving car, one powered by really cutting-edge AI. It's confidently navigating a busy city street. Seems flawless, right? A real marvel of engineering, taking us safely where we need to go, well, almost every single time. But then, what about that minuscule, almost imperceptible glitch? Maybe it's just a single rogue pixel in the camera feed, or, I don't know, a momentary flicker in the streetlights, barely noticeable, or even just a speck of dust landing on a critical sensor. Suddenly, in a fraction of a second, this tiny, unseen little perturbation could cause the car to swerve unexpectedly, pushing it suddenly into an unsafe situation, maybe even, towards a dangerous collision. We're not just talking about minor errors here. We're really digging into the critical, sometimes life and death difference between near-perfect performance and absolute unshakable reliability, especially when human lives are on the line. And this isn't just some futuristic scenario about robots. It's fundamentally about the profound trust we are increasingly placing in these artificial intelligence systems, the ones quietly weaving themselves into, well, pretty much every aspect of our daily lives.
That scenario you paint, it perfectly encapsulates the core challenge facing artificial intelligence today, particularly in this rapidly evolving realm of reinforcement learning, or RL. Now, while deep reinforcement learning, DRL, has undeniably achieved truly superhuman feats in highly controlled environments. Think about AlphaGo mastering Go, or agents conquering complex games like StarCraft. And it shows immense promise in real-world areas like robotics, logistics, and yes, autonomous driving. The problem is, these systems still often remain what we critically call black boxes. Their decision-making processes are frequently opaque. It's incredibly difficult for us to understand the why behind their actions, and they're notoriously vulnerable to what are termed adversarial perturbations, those minuscule, almost imperceptible changes in input that can, just like you described, lead to catastrophic, unpredictable failures. The stakes in these real-world applications are not just a lost game or a few points deducted. They involve genuine human safety, security, and the absolute robustness of the system in unpredictable environments. We're talking about systems where a failure isn't just an inconvenience. It's a genuine, potentially life-threatening danger.
Right. So given this huge challenge, how do we even begin to shine a light into these really complex black boxes? How do we move beyond just sort of hoping that a learned policy is safe to actually being able to verify its safety and robustness with a high degree of confidence, maybe even, like you said, a mathematical guarantee? Well, today we're taking a deep dive into a truly groundbreaking new framework that aims to do exactly that. We're looking at this fascinating paper by Ahmed Nasir and Abdelafid Zanati that proposes a radically different way of thinking. Instead of seeing the interaction between an RL agent and its environment as just a series of isolated, discrete decisions, they model it as a continuous, discrete-time, autonomous, dynamical system. So by borrowing these powerful analytical tools from a completely different scientific field, the study of dynamic systems, they've forged a novel way to visualize, quantify, and maybe even guarantee the safety and reliability of learned policies. This approach, I think, offers a really profound shift in perspective. We've just touched on the incredible triumphs of deep reinforcement learning, DRL, right? It's truly revolutionized what we thought AI could do, from game mastering feats to guiding sophisticated robots. But you also brought up this critical and, frankly, kind of unsettling vulnerability. What exactly is the knowledge gap this paper is trying to fill? Why is this kind of rigorous verification so urgently needed now more than ever, especially as AI moves from games into our actual lives?
Precisely. While DRL agents excel in those pristine, often perfectly simulated environments where they're trained, deploying them into safety-critical real-world systems. Autonomous navigation for cars, highly precise surgical robots, maybe drone delivery systems that requires far more than just achieving high reward scores during training. The authors of this paper, Ahmed Nasir and Abdelafid Zanati, they really hone in on a crucial, persistent gap. Current methods, while powerful for optimizing performance, often rely heavily on statistical assumptions. Think of it like saying, well, 99.9% of our tests work perfectly, so it's probably fine. But for a self-driving car, that remaining 0.1%, that could represent a catastrophic failure, right? Or these methods can be so computationally intensive that they simply can't provide real-time assurances for complex dynamic scenarios, which means they often lack the intuitive, formal, and deterministic guarantees needed for true, unshakable, real-world deployment. The fundamental issue is this black box nature of deep neural networks. We don't genuinely understand why an agent makes a specific decision in a complex situation. And that makes building public trust incredibly difficult, maybe even impossible, when you can't trace the logic or predict its behavior under new circumstances. Researchers across the field, they've highlighted this problem of opaque decision-making and the significant impact of adversarial perturbations as a widely recognized and critical hurdle in AI research. This framework is a game changer because it moves beyond statistical likelihood to offer deterministic, interpretable, and formal guarantees that have been largely missing. It's a fundamental shift in how we approach proving an AI's safety, giving us a level of certainty that's been largely missing, especially concerning the impact of those minuscule, often imperceptible adversarial perturbations, those tiny changes to an agent's input that can completely throw it off course, which are a major, major concern.
So, it sounds like it's about much more than just whether an AI performs well on average. It's about knowing not just if it works, but understanding why it works the way it does and how reliably it works even when things inevitably go a little off script in the real world. It's not enough for it to mostly work. It has to always work safely, even when faced with unexpected noise or slight variations.
Exactly. The paper's central premise is quite transformative, actually. By modeling the combined RL agent and its environment as a single, coherent, dynamical system, we can fundamentally change our analytical lens. This allows us to analyze the inherent geometry of the agent's behavior within the state space, that vast, multidimensional map of all possible situations the agent can find itself in. The authors explicitly state, our central premise is that the combination of a deterministic RL policy and its environment constitutes a discrete time autonomous dynamical system. This means we can uncover and understand the underlying structural patterns that govern how trajectories evolve over time, revealing hidden safety barriers and potential failure modes that simple reward accumulation metrics would simply never expose. It's like moving from just watching a single car drive along a road to looking at the entire topological landscape, the roads, mountains, valleys, rivers, understanding all the possible paths and where they might lead.
Okay, so we're treating the agent and environment as this single, unified, dynamical system. That still sounds a bit abstract, maybe, for those of us who aren't mathematicians or physicists. How do they actually go about analyzing this complex system? What's the core tool they use to map out this intricate landscape of an AI's behavior and predict its movements?
Okay, the key analytical tool here is something called the finite time Lyapunov exponent, or FTLE. To make it more intuitive, let's use an analogy. Imagine you're standing by a river, right? And you drop two tiny, almost identical leaves into the water at nearly the exact same spot. Now, if the water flows smoothly and predictably, those two leaves will probably stay close together for a while, following similar paths. But if there are turbulent currents, hidden eddies, or strong diverging flows, those leaves will rapidly separate and diverge, going their own distinct ways. The FTLE measures exactly this phenomenon. It quantifies the maximal rate at which initially close trajectories separate over a finite time window. It's a powerful way to quantify how sensitive a dynamic system is to minuscule changes in its starting conditions or initial state. A high FTLE value indicates an area where even tiny uncertainties can lead to vastly different outcomes down the line.
Okay, I think I get it. So it's like a super sophisticated river map for AI behavior. It doesn't just show you the most likely path the AI will take, but crucially, it highlights where the currents are strong, where things are pushing apart, indicating unpredictability, perhaps, and where they're pulling together, showing predictable convergence. So it's like a special current detector that highlights areas of extreme divergence or tight convergence in the AI's decision space, telling you where the behavior becomes unpredictable or where it's tightly controlled. Is that kind of the idea?
That's a fantastic analogy. Truly insightful. You've captured it perfectly. And what's even more remarkable is that the ridges, the peaks, where these FTLE values are highest, they reveal what authors call Lagrangian coherent structures, or LCS. As the authors eloquently put it, these structures function as the hidden skeleton of the dynamics. Picture the vast landscape of possible decisions an AI can make, its entire state space. These LCS are like the major mountain ranges, the watersheds, the great river divides on that landscape. They're not physical walls or static boundaries, but dynamic barriers and pathways that fundamentally govern how trajectories flow, where the agent moves, and ultimately where it's likely to end up. They essentially partition the state space into distinct regions, dictating the overall transport and mixing properties of the system. Understanding these structures is absolutely critical for understanding both the safety and the robustness of any AI policy. And the true genius of this framework lies in how these Lagrangian coherent structures map directly and intuitively critical policy properties that we really care about in AI safety. So first, we have repelling LTS for safety.
The authors explain that repelling LCS function as dynamical barriers or divides that nearby trajectories cannot cross. Think of them as invisible lines of no return, or maybe dynamic force fields. For a truly safe policy, we would hypothesize and then use this framework to verify that the agent must learn to actively create and maintain strong, repelling LCS, ones that effectively wall off obstacles in unsafe regions of the state space. This provides a clear visual confirmation of the agent's learned avoidance strategy. If you see a bright, prominent ridge of high FTLE values forming along a wall or around a hazardous area, it tells you, pretty unequivocally, that the agent has learned to actively steer clear of it. It's a very visual, very unambiguous indication of embedded safety. Then conversely, we also have attracting LCS for robustness. These are, in a sense, the opposite of repelling LCS. The paper notes attracting LCS function as dynamical highways or collectors that attract and guide nearby trajectories. For a truly robust policy, one that reliably achieves its goal without getting sidetracked, we should ideally see a single dominant basin of attraction that leads directly to the desired goal state. If, however, there are other strong attracting LCS elsewhere in the state space, well, that flags potential trap states, or suboptimal loops where the agent might get stuck, indicating a significant lack of robustness. It's like finding a series of powerful whirlpools in our river analogy that pull the agent into undesirable holding patterns, preventing it from flowing smoothly to its intended destination. These are the hidden pitfalls we need to identify and ideally eliminate.
Okay, so we can actually visualize these dynamic safety barriers and these powerful attraction points, these highways and whirlpools in the AI's decision-making landscape. That's incredibly intuitive. I can almost picture the AI's internal brain having these invisible lines and currents guiding its behavior. But visualization is one thing, right? How do they move beyond that qualitative understanding to something you can actually measure, something you can compare objectively across different policies, or even track the improvement of a single policy during its training? We need hard numbers, something quantifiable, don't we?
Absolutely, you're spot on. And that's precisely where their novel quantitative metrics come in, building directly on the FTLE and the detailed trajectory analysis we just discussed. As highlighted in their main contributions, the authors introduced three crucial distinct metrics: mean boundary repulsion, MBR, aggregated spurious attractor strength, ASASs, and temporally aware spurious attractor strength, TASAS. These are specifically designed to provide scalar, objective numerical measures of a policy's safety margin and its overall robustness. Moving beyond just what we can see visually to what we can truly quantify and compare, this is a really crucial step towards engineering trustworthy AI. Okay, let's delve into the first one, mean boundary repulsion, MBR. This metric directly quantifies how strongly the policy repels the agent from unsafe regions. Think of it like measuring the strength of a security perimeter around a danger zone. MBR measures the average strength of that perimeter. A high MBR score signifies a strong, robust safety barrier, indicating the agent has learned to actively keep its distance from danger. The authors define MBR as the arithmetic mean of the 4-time FTLE values on this boundary, specifically referring to the boundary of an unsafe region. Essentially, they identify all the states immediately adjacent to an unsafe area, simulate trajectories starting from those states, and then average the FTLE values in those critical boundary states. This gives us a single, measurable number for how well the agent walls off danger, literally quantifying its commitment to avoidance.
Okay. So if a policy has a high MBR, it's effectively screaming, stay away from danger zones, or like a truly impenetrable force field that it's learned to put up. The paper mentions a simple wall environment where an agent's only job is to learn to avoid hitting a wall. How did MBR evolve there as the agent learned? What did that tell them?
Yeah, exactly. That's a perfect way to visualize it, the strength of that dynamic force field. And in their experiments with a deep Q network, a DQN agent, learning in that simple wall environment, the MBR score tells a very clear and compelling story. Early in training, like at episode 0, the MBR was this chaotic 0.00040, basically nothing, indicating almost no discernible repulsion from the wall. The agent was just bumping into it randomly. But as the agent learned over time, the MBR score climbed steadily. It reached a robust 0.0994 by episode 1200. This dramatic increase quantitatively confirmed the visual evidence seen in the paper's figures, where you could actually see a strong, distinct, repelling LCS forming precisely along the wall's boundary. It showed that the agent wasn't just lucky in avoiding the wall, it had learned to actively and predictably stay away from the obstacle. This is a very concrete, measurable indication of learned safety, a stark contrast to older methods that might just report something vague like a low collision rate.
Got it. So MBR gives us a clear, actionable score for how effectively an AI builds these invisible keep-out zones around obstacles, or how strongly it resists entering dangerous areas. That's a practical and incredibly valuable measure of safety, something we can actually track, compare, and use to validate an agent's behavior.
Okay, moving on. For assessing a policy's robustness, its ability to reliably reach its goal without getting sidetracked, we introduce aggregated spurious attractor strength, ASAS, and temporally aware spurious attractor strength, PASAS. ASAS measures the overall combined pull of all unintended attractors relative to the desired goal attractor. The authors formulate it as a simple ratio. ASAS equals High spurious divided by ASCO, where AS is the maximum density in the goal region, and High spurious is the sum density of all other significant attractor peaks outside the goal. So a low ASAS is ideally near zero. That means the agent is strongly focused on the desired goal and not being pulled into other alluring but ultimately incorrect states. If, in a worst-case scenario, the goal is never reached or ACE goal is zero, ASAS is defined as infinity, indicating a complete failure to find the goal.
Okay, so if ASAS is high, it essentially means the agent is getting pulled in a lot of different, potentially wrong directions, not just definitively toward its goal. Like there are too many appealing but misleading off-ramps on the highway when you're trying to get to a very specific destination.
Precisely. It clearly flags the presence and strength of these off-ramps or detours. But here's where TASIS refines that, offering a crucial and incredibly insightful distinction. ATAS by itself can flag what might appear to be highways that eventually do lead to the goal, even if they look like temporary detours or transient attractions. TASIS, however, is designed specifically to distinguish between these transient pathways, which might be perfectly acceptable parts of a robust strategy, and genuine terminal trap states, where the agent gets permanently stuck. It achieves this by weighting each spurious attractor's strength by a persistence factor, denoted as P. This persistence factor is calculated as 1 minus the escape ratio EP, where EP is the fraction of trajectories that, starting from that spurious attractor, actually manage to escape and reach the goal eventually. So essentially, TASIS asks a critical question. If an agent gets to one of these unintended attractors, does it eventually escape to the goal, or does it get permanently stuck there, trapped indefinitely? Therefore, a non-zero TASIS score unequivocally confirms the existence of at least one genuine terminal trap region from which the agent cannot escape to the goal.
Right, okay, this is where it gets truly fascinating. The paper describes a U-shaped trap environment. It sounds like it's specifically designed to be deceptive, where the most obvious path might actually lead to a dead end. What did ASAS and TASIS reveal about the policy's robustness there? And why was TASIS so incredibly important for correctly interpreting the results in this tricky scenario?
Yes, this U-shaped trap environment was, as you suggest, a brilliant and cunning test case, meticulously designed to trick the agent into a local optimum, a seemingly good path that wasn't the true ultimate goal. At episode 1200, when the agent had supposedly learned, the AC's value was relatively high, 1.2258. Now, on its own, this might initially suggest poor robustness because it implies the combined pull of spurious attractors was actually stronger than the pull of the goal itself. However, and this is the absolute crucial part, the TASIS metric plummets dramatically to just 0.0727. This is a monumental distinction. It demonstrated unequivocally that while there were indeed attracting highways or detours, as indicated by the high ASIS, they were merely transient waypoints that eventually led to the goal. They were not terminal traps where the agent would get permanently stuck. Without the refined insight provided by TASIS, one might falsely conclude that the policy was flawed and unreliable, when in reality it was simply taking a longer but ultimately successful route. This really highlights the framework's power to reveal true policy robustness, moving beyond just superficial metrics.
Wow, okay, so ASAS tells you that there are other attractive routes or detours, but TASIS, that truly clever addition, tells you if those routes are actually dead ends or just temporary scenic detours. That's a huge aha moment for truly understanding robustness. It's like finding out a winding country road eventually gets you to your destination instead of leading you into a permanent, inescapable traffic loop. That's brilliant.
Exactly. And the framework isn't limited to simple grid worlds or toy problems either. It scales and provides critical insights even in complex, continuous control problems. The authors applied it to the lunar lander continuous V2 environment. This presents a much more challenging 8-dimensional control problem, where the agent has to learn to precisely land a spacecraft. Now, to make the complex dynamics visualizable and analyzable, they examined a 2D slice of this 8-dimensional state space. This slice corresponded to the lander's XY position, holding other critical state variables like velocities and angles at zero. This allowed them to focus on a critical phase, like descent or hovering near the landing pad.
Right. And what did their analysis reveal about the lunar lander policy?
Was it as robust as one might hope for such a complex and delicate task? Especially thinking about the real-world implications of a moonlander mission.
Well, this is where the framework truly shines its diagnostic light, I think. It uncovered a critical flaw, a flaw that standard reward-based metrics, which might just report a certain percentage of successful landings, would completely miss. The FTLE field, which visually represents the system's sensitivity, it was noisy. It lacked the strong, coherent safety barriers we saw in robust policies, like, say, those developed for the mountain car environment. More damningly, the attractor plot, which shows where trajectories tend to converge, revealed something quite alarming. While a desirable attractor did exist at the goal, the landing pad, two powerful, spurious attractor highways absolutely dominated the flow. These effectively pulled trajectories away from the intended landing pad into undesirable looping patterns. These weren't deficient routes to the goal. They were diversions that essentially prevented the lander from achieving a precise, controlled touchdown. Quantitatively, this lunar lander policy yielded an SS score of 3.9038, and critically, a TESSA score of an identical 3.9038. Now, an ASAS value greater than 1.0 already indicates what the authors call extremely poor robustness, meaning the cumulative pull of the spurious unintended attractors is significantly stronger than the goal's pull. The fact that the TASAS score was also 3.9038 unequivocally confirmed that these were not just transient detours that the lander might eventually escape from, they were persistent terminal traps from which the agent utterly failed to escape. So this policy, despite potentially getting some good rewards, maybe by crash landing somewhere or just getting very close, was demonstrably unsafe and profoundly unreliable for precise goal-oriented landing. This vividly demonstrates the framework's diagnostic power to uncover critical hidden failure modes that could have truly disastrous real-world consequences.
So this framework acts like an incredibly powerful diagnostic tool then, finding the hidden flaws in AI policies that might look perfectly acceptable on the surface, maybe even scoring high in simulations, but are actually death traps or dangerous detours in disguise. It's like an X-ray for AI behavior, revealing the broken bones and hidden pathologies beneath the skin that reward scores alone could never show. That's a huge step forward for genuine trust in AI systems.
Indeed it is. And beyond just diagnostics and visualization, the framework takes another monumental step. It offers a way to provide formal guarantees of local stability. This is a truly big deal for safety-critical systems. In specific regions of the state space where the FTLE is consistently low, indicating inherently stable behavior where trajectories tend to stay close together, they can mathematically prove that initially close trajectories will remain close. This is formally captured by Proposition 3.1 in the paper, which they term bounded divergence. It's not just an observation or a statistical likelihood. It's a rigorous mathematical statement about how much trajectories can separate under certain conditions.
Hold on, so this isn't just an observation or a prediction, it's a mathematical promise, a formal certification of stability for certain behaviors. That's an incredibly strong claim for AI, something we rarely hear.
Yes, exactly. It is a strong claim, and a significant one. For the pendulum V1 environment, for instance, where the goal is for the agent to learn to balance an inverted pendulum upright at its unstable equilibrium point. They define a stable convex region directly around that goal state. Using the calculated maximum FTLE within this specific region, which they found to be approximately 0.7158 over an integration time of 20 steps, they could formally certify the policy's behavior. Specifically, the paper states that for any desired final separation tolerance, POS 0.05, the policy is robust to any initial state perturbation smaller than 3.00 tentate. What this means, in practice, is that if your initial state of the pendulum is off by less than that tiny delta, 3.08 tentate, you are mathematically guaranteed that after 20 time steps, the final state of the pendulum will be within 0.05 of where it should be, stably balanced. Now, while the allowed perturbation might seem incredibly small due to the exponential nature of the Lie-Prinoff bound, the critical point here is that it's a concrete, formal guarantee of the policy's stability near its equilibrium point. This fundamentally moves us from statistical confidence, like saying, it worked 99.9% of the time in our thousands of tests, to actual mathematical certainty in specific, well-defined contexts. This level of rigorous assurance is absolutely crucial for applications where errors, no matter how small, simply aren't acceptable. The paper visually represents this certified stable region overlaid on the attractor field, offering a clear picture of exactly where these guarantees apply.
So it's not just about identifying problems anymore, but about actually certifying safety and stability in defined zones. That's monumental for critical applications where even a tiny deviation or unexpected behavior could be catastrophic. This is the kind of rigorous assurance and deterministic understanding we absolutely need for AI to be truly integrated and trusted in the real world. Feels like a real step
That's
forward. This has truly been a comprehensive and really eye-opening way to look at RL policies, going far beyond just surface-level
Yeah.
performance. For you, what are the most exciting, maybe the most concrete applications of this framework that could make a real tangible difference in how we build, deploy, and ultimately trust AI in our everyday lives? Where do you see it having the biggest impact first?
That's a great question. There are two immediate and profoundly impactful applications that immediately spring to mind for me. First, and perhaps most critically, is pre-deployment verification for safety-critical systems. Before we ever allow an AI agent to operate in a self-driving car on public roads, or to control a medical device inside a hospital, or maybe guide a critical drone during an inspection, this framework empowers us to formally verify its safety and robustness beforehand. It goes far beyond simply training a model until it achieves high reward scores in some simulated environment. It provides a deterministic, interpretable assessment that can proactively uncover critical hidden flaws and vulnerabilities, just like those we saw in the lunar lander example, before they ever lead to real-world accidents, property damage, or put human lives at risk. This is about building essential, foundational trust in autonomous systems, moving from hopeful assumptions to verifiable certainty long before they ever leave the lab. The second major application is equally powerful, I think. It serves as an exceptional diagnostic tool for policy improvement. Imagine an AI developer struggling to debug a complex RL agent. Maybe it isn't performing as expected in the real world, even if it aced all its simulations and achieved high rewards. This framework provides an intuitive visual and quantitative diagnostic roadmap. If a policy isn't robust, the MBR, ACES, and TASTAS metrics can tell you precisely why. Are the safety barriers around obstacles weak or non-existent? Or are there too many spurious attractors pulling the agent off course? And, crucially, are those attractors merely temporary detours that eventually lead to the goal, or are they permanent, inescapable traps? This granular level of insight is invaluable. It can directly guide developers in redesigning or retraining policies to systematically eliminate specific vulnerabilities rather than just engaging in guesswork or trial and error. This translates directly into safer products, less frustrating AI experiences for us as users, and ultimately a more confident and responsible deployment of these powerful systems into society. It's like giving engineers an MRI scanner for their AI's decision-making process.
Those applications are incredibly compelling. It really does feel like a missing piece in the AI safety puzzle. But of course, like any powerful new framework, the authors themselves identify areas for future work and inherent limitations, right? I mean, nothing is a magic bullet that solves everything overnight. What are some of the boundaries of this current work?
That's absolutely right, and the authors are very transparent and pragmatic about the current boundaries of their work. It's important. They acknowledge that the current analysis is specifically designed for deterministic systems, meaning systems where, given the same state and action, the outcome is always precisely the same. Extending it to stochastic systems, where actions or environment transitions have an element of inherent randomness and unpredictability, which, let's face it, is a much more accurate description of the real world. That's a key and significant next step. As they explicitly state in their conclusion, future work could extend this analysis to stochastic systems. This is a profound challenge because introducing randomness fundamentally changes how you define and calculate concepts like FTLE and attractors. It gets much harder. Another significant challenge lies in computational efficiency for very high-dimensional state spaces. While they successfully demonstrated how to apply their analysis to 2D slices of complex continuous environments, like our lunar lander example, a full comprehensive analysis of environments with many, many dimensions, think dozens or even hundreds of state variables, that remains a substantial computational hurdle. The calculations for FTLE and identifying LCS can become incredibly intensive as the number of state variables increases exponentially. The paper mentions this directly, suggesting that future work should develop more computationally efficient methods for high-dimensional state spaces. It's an area that will require some innovative algorithmic development for sure.
Okay, so it's incredibly powerful for what it does do, offering these deep, verifiable insights into deterministic systems. But it's not yet a magic bullet for every single AI system out there, especially those with inherent unpredictability or immense complexity that can't easily be reduced to a lower dimensional slice. It still needs further evolution to truly generalize across all AI applications, it sounds like.
Exactly. But it's a crucial and foundational step forward. It provides a completely new analytical lens and a rigorous set of tools that were previously unavailable. It offers a solid starting point, a robust methodology for building greater trust. And looking ahead, the authors propose several fascinating avenues for further research that could unlock even more of this framework's potential. One incredibly promising direction, for instance, is to use this framework not just for post hoc analysis, analyzing a policy after it's already been trained, but to guide policy training directly. Imagine having these safety and robustness metrics like MBR and TASIS integrated into the training loop itself. This would allow the agent to learn safer and more robust behaviors from the outset, actively optimizing not just for rewards, but for verifiable safety and robustness, rather than simply identifying problems after the fact. This proactive, safety-first approach could be truly revolutionary in how we train AI systems. And of course, they also suggest continued efforts to develop those more computationally efficient methods for handling high-dimensional state spaces, as we discussed. If these methods become more scalable and accessible, it would open up even broader applications for this framework across virtually all domains of AI, maybe from climate modeling to drug discovery, who knows?
This deep dive really highlights how interdisciplinary thinking, bringing tools from seemingly disparate fields like dynamical systems theory into the empirical world of reinforcement learning, can tackle some of the most pressing and complex challenges in AI today. By bridging the empirical success of reinforcement learning with the rigorous mathematical demands of formal verification, this dynamical systems perspective offers a critical new tool, a tool for building truly trustworthy and reliable autonomous systems. It moves us from merely hoping our AI is safe to actually being able to know it is, at least in defined, verifiable contexts. That is a profound shift, a really important one. So this framework isn't just about verifying AI, it's about fundamentally pushing the boundaries of what we can expect from intelligent systems, demanding a new level of accountability and understanding. If we can formally guarantee safety and robustness in complex AI policies, what other areas of engineering or science, or maybe even human decision-making, could benefit from applying a similar dynamical systems lens? What if this kind of rigorous structural verification became a standard, not just for artificial intelligence, but for any complex system where trust, predictability, and safety are absolutely paramount? It's something truly worth pondering on your next journey.